I guess we'll start. It's almost to 5, and people can keep joining. That's all right. So, hi everyone. I'm Reena Dayal. I head I'm the chair for the Quantum Ecosystems and Technology Council of India. And the QETCI, as we call it, is actually an industry body which is trying to bring the ecosystem in quantum together so that we can not just act as a catalyst but sort of look at the areas that can benefit from our intervention. So in some senses, we are a think tank as well as an enabling organization. So we are also getting involved in making recommendations for policies, looking at where the gaps are in the ecosystem and how we can fill those gaps. Now, today we have a session scheduled on it's a workshop on quantum computing on Amazon Braket. Amazon is one of the voting members, one of the large, technology companies working in the quantum space, which is also a member of QETCI. And this is the first of a series of sessions that we are planning. So we will have sessions from other companies like Microsoft, Google, etc., that are lined up. And this effort is an awareness building effort. We also have something called an education committee, which is focused more on how the education has to transform in the quantum space in India, both at an undergrad, postgrad, and at a PhD level. And also in terms of how things have to change, what are the things that can be done for better workforce building and how can more transparency be brought in from that perspective. There is an opportunity for people, if you're part of some of the member companies, you automatically can reach out and ask for getting added to the mailing list. But if you're not, and as an individual, you want to apply for membership, you can go to the website and, send out an email, subscribe, and that can be done so that if you want to stay connected to the ecosystem, that's one thing that you can do. So I thought I'd, sort of mention that right now. Share feedback after you go through these sessions, not just today's session, but the next ones that are coming up as well. Do share feedback with us, which is constructive and which tells us how you want to let QETCI and entities like Amazon help you in this space better, right? So feedback is very, very welcome. The rules that are we going to, given that there is a large number of people, there are around close to 50 people on this call right now. Around 100 had subscribed, so there might be more people joining in the interim. My request to all of you would be is to stay on mute. Let Sachin, let our instructor run through the session, and I'll introduce him in a second. Session. And then if you have any questions, please do go ahead and start typing those questions on the chat window as and when they come to your mind. When we will take breaks in between to address those questions in a systematic manner, right? So that's the approach that we will follow. And with that, I'm going to request Sachin Punyani to actually go ahead and do a brief introduction of himself and Amazon Braket, and then do a deep dive into the session itself. Sachin, over to you. Are you able to? Okay, but how did you get muted again? That's like pretty strange. Let me just let me remove that. Can you try now, Sachin? Yeah. You can speak now, Sachin. I think you are unmuted.
Yeah. Can you hear me now?
Yes, and I have changed the security settings. People can unmute themselves, but my request to everyone would be, please do not unmute during the time when Sachin is speaking.
Sure. Thanks. Thank you very much, Reena, for setting up the context. Hello, everyone. And thank you, QET-CI, for setting up this platform actually to create awareness about the quantum computing, bringing people up to speed with the quantum computing thread that is happening in the world around now. So I'm Sachin. By my role, I work on the solutions and the business development for the deep tech in AWS for various threads. So the AIML, analytics, HPC, and for quantum computing, it's the evangelism role and the ambassador role that I'm playing. So just before moving into the details of this quantum computing session, just want to share one thing. There is a myth around quantum computing that you need to be a PhD in quantum mechanics or some other degrees to start with. I am a hardcore commerce graduate. Of course, I have a computer science degree as well, but I am not a PhD in quantum mechanics or quantum physics. So I'm able to follow things in the quantum computing, do my activities or programming in the quantum computing. So it's just wanted to break that myth as well as we go along. Also, we'll try to cover, while we are introducing quantum computing today, we are trying to answer multiple questions. We will try to avoid mathematics as much as possible, and also we'll cover the points from the concept standpoint so that people understand the concepts and they are able to jump into the quantum computing scenario faster. So these are the questions that we will try to answer. We'll set up the context. Also, like Reena set up the context, this is an awareness session. So we'll try to build up the concepts. We'll try to cover some part of the some demos or some walkthroughs of some of the code pieces. But overall, before getting into that, we'll spend some time in setting up the concept so that you can follow what exactly is happening in this thread. So we'll answer what is quantum computing, where exactly it is applicable and how it is different from the classical computers that we have right now, how to build the expertise, and what is the AWS approach towards quantum computing, because AWS has a separate service for Amazon Braket for quantum computing. So what value add Braket is complete quantum computing ecosystem, and now how to, I mean, why you should invest time now on the quantum computing and what you should expect from your time investments there. So all these questions we'll try to answer. So just starting on that. So before we get into detail, just starting from the mindset that where exactly the current quantum computing ecosystem, where exactly can it be leveraged, the potential applications. If you see, the applications exist across industries. But if you see very carefully, I mean, of course, logistics, agriculture, machine learning, finance, everywhere we're talking. But if you look at the problem statements where it is immediately applicable or where immediate effort can be put into solve bigger problems, it is, if you see traffic routing or network optimization in logistics, if you see portfolio selection in finance, or if you see machine learning scenarios. So most of them you will see are optimization problems, or maybe some problems which are so hard to be solved by a classical computer. So hard when we say the classical computer take much longer time to solve those problems, or maybe it might not solve either in our lifetime. So those kind of problems where we can target. Those are the problems which we can target with quantum computers. We'll cover some more details why exactly quantum computers are meant to solve these problems. We'll cover those points so that you can relate these scenarios. So before moving into that, what exactly is a quantum computer? We'll build up these concepts. Precise, see, there are a large number of definitions. Trying to bring it to few words. There might be many other definitions as well, but in a generic term, it's a computer that can solve your problems or that can do the calculations following the quantum laws of quantum mechanics. If we look at the, if we think of the classical computer, the laptops, the servers that we have, normally some voltage is passed through circuits. I'm going little technical now. Normally a voltage is passed through those circuits, through those semiconductor circuits, and there is a voltage threshold where when this voltage goes beyond a threshold, we call it a 1, and when the voltage goes remains below a threshold, we call it a 0. So it's a binary system. We say there is a bit, there is 0 and 1. So there is a semiconductor voltage is being passed. That basic mechanism of calculation or computation is changing in the quantum computer. So when the basic platform thought process is changing, of course, the ecosystem on top of that will also get impacted, will change. The ways to write softwares, ways to build the applications will also change. So now we'll try to understand what exactly is happening, what is different from the classical computer. So where we just said that it is solving the problem which are not easy for the quantum computers. Still there exist few problems which might be hard for quantum and the classical computers both. But overall, the problems that can be solved by classical computers are kind of superset by the quantum computers are kind of superset of the classical computers. To what extent? So this is the, and that is why too much energy, effort, cost is being spent. So if you see, as the problem size increases, the fastest supercomputer or the classical computer, as we say, might take hundreds of years or maybe many, many years to solve that problem. We have heard about the time complexity, like the order of n square, order of n cube, and many polynomial level of complexities. But when it comes to the quantum computer, those typical optimization problems or some other problems that we are going to talk about, they can be, I mean, this could be the time difference. The 100 years can come to 1 minute, and the speed up is not just 10x. It's not just frequency getting increased of the processor frequency getting increased. It's like jump happens in terms of 10 raised to power x. So this is the value add that scientists and researchers see in quantum computing, and that's why they are putting so much effort, because huge number of problems that are currently not solvable within the lifespan of a person can be solved, and we can bring those, if we bring those solutions to real life, our business problems, business solutions will become much more mature, much better. That's why so much effort is being put. Now, some touch on the hardware side, one part, because in the classical computers, we know that there is a hardware, there is a system which is working on bits. Then, of course, there are some compilers, tools on top of that, programming languages on top of that, using which you write the applications. So same thing here as well. You have some level of hardware, and then on top of that, you will have some tooling available to write programs for that system. In the classical computers have now standardized. We all know they are on 0, 1, we discussed. But the newer scenario, which is different from that bit, is being brought in by multiple different ways of the quantum system. So people follow, I mean, some computers are following superconducting approach, some are following trapped ions. For example, IonQ follows trapped ion. Some research was also done on Rydberg atoms, and the recent one, which brings the cost and of the quantum computers down, the quantum hardware down, is through photonics. So different experiments are being done, or different improvements are being done to bring robustness to the underlying hardware. Not going in much detail of the hardware technology here, just moving immediately to the concept change that quantum computers are bringing from the application standpoint, or from the overall computation standpoint. So that is where the difference comes. We said that classical bits or classical systems are binary, so they have 0 or 1. So they can, I mean, every bit in the classical system will have value either 0 or 1. The major concept change or major thought process change comes from the quantum system is, this is called a quantum bit. Instead of having a binary ecosystem, now if you perceive a sphere, a 3D sphere, now this qubit can have any value, qubit can have a value anywhere in this sphere. It can be the North Pole, it can be the South Pole, it can be this way. It can change the rotations. The arrows can go up, down, in any direction, because it's a 3D sphere, so it can assume any value. That means instead of having 0 and 1, 2 binary values, it can also have values somewhere between 0 and 1. It can have value, so it can have different values, which is called superposition. That means it need not be discrete. It can be any value. So some part of the, or some ratio of the 0 it carries, some ratio of the 1 it carries. So it might be some calculation based on that. So that is called superposition. That means instead of binary, it has value which is made of combination of 0 and 1 or multiple other values put together. So that's the major thought process change. Now, what could be the changes in the value? We said we can assume value in multiple directions of that sphere. So if you just look at this sphere in the 3-dimension, so it can be like the value spins up the arrow or the value spins down. So accordingly, some expressions change. I'll just go back to the previous slide. So here you are looking at this as 0. Now, because it can have multiple values, we'll cover to that point. But this notation that you see here, the bar and the arrow, this actually is a vector because it can have multiple values. We'll see what vector signifies. It's a typical vector in the mathematical vector space you talk about. So it carries a value. So because it's a single qubit here, so single value you are seeing. So when you have multiple values put together, so some part of 1, some part of 0, if you spin it down, again, some operation happening. You can also rotate it leftwards. You can also rotate this sphere rightwards. So this is the concept or thought process of the underlying qubit. It's not a bit or a binary digit in a classical computer. This is the formation of qubit, the basic unit of a quantum system. And again, you're rotating it. So which side are you rotating it, outwards or inwards? Accordingly, the bit value changes. So this is a change in bit value. So if you see one single bit, if you want to see that how much storage or how much value does one qubit carry. So it's some part of 0, some part of 1. That means you need, if you want to map it to the classical computer, you need 2 bits to you will need 2 bits to store 2 classical bits equivalent to store information in one single qubit. Now, this is, we saw like multiple dimensions changing. 0, the north pole representing like a vector, we said 1, 0, 1, the south pole being represented, and there can be huge number of values. This is just a signifying. We are not going into maths, but just trying to create a concept that this bit or this qubit can carry any of those values or even many more values, because they can point to, that can be point on this sphere anywhere. So that's one qubit basically. If you have any query anywhere, please do write in the chat pod. We'll take a logical break at a place and we'll try to answer those queries. Now, we did talk about one qubit. Now, how it happens when there are more than one qubits? So superposition is the concept where we say that the value can be anywhere between 0 and 1 on that sphere. When you have multiple qubits, that 0 that we talked about actually changes to multiple values. That's why it is vector. That in a classical computer, if you have 2 bits, these 2 bits are independent. If you change a bit, second bit is completely independent. Or if you have 4 bits, you can change any one of the bits, but without impacting the other bits. While in quantum computer, if you have a quantum computer with say 8 qubits, then the entire state of the quantum computer is represented by a vector. So you cannot have a scenario where you change 1 qubit and you and all other 7 qubits in that 8-bit quantum computer are not unimpacted. These states, if you see, as you add more qubits to the quantum computer, the vector or the entire quantum computer state becomes even more bigger, representing various combinations of both the bits. Now, if we just add more bits here, say if we make 3-qubit quantum computer, then this quantum computer state will become even more based on the vector state of all 3 qubits. So there will be total 8 numbers or 8 scenarios that it will record in the quantum computer state. Now, if you see, if we keep on adding more qubits slowly, if you see like a 53 qubit quantum processor, that means a quantum computer with which supports 53 qubit, it will carry, the quantum computer state will carry information roughly around 10 million or billion data points. Basically, that's somewhere approximately in petabytes. So that is the level or that is the scale at which quantum computer operates. Now, in classical computer, we have few bits. We have the instructions that operate on those bits. So those bits change. while whatever operations we are going to perform on qubits, immediately this level of data or this amount of data will be processed. So that is what is bringing in the speed and the power or parallelism or the power of the quantum computer to solve the problem. So this is the basic difference. Now, just taking, I mean, because we have covered some concept. Now, how, is it, how is quantum computer becoming faster? Is it because it is running things in parallel? Now, looking at the concepts that we have done, actually not, it's not the parallelism that it is bringing. It is the superposition and entanglement. Now, what exactly is entanglement? Go just back to, sorry, this statement. If you see, we said that two qubits, if you have, they make the entire quantum computing state. That means they are entangled together. These bits are not, these qubits are not separate, isolated, independent. As you keep on adding more qubits, they make a quantum computer state or quantum system state. So bits are completely entangled. Now, if you perform any operation on this quantum system, entire state of the quantum system will be modified. That entanglement, that one single operation will be impacting the entire state, all the processing will happen, and that exactly is bringing in the speed in the quantum computer that we said that it can achieve what classical computer can achieve in 100 years, it can achieve in a minute, because a single instruction or maybe few instructions on the quantum computing state can process huge amount of data. That's the power, and that is how it is bringing in the speed. Now, when the basic thought process has changed, that simply means the algorithms that will be written for these computers will be quite different. And this opens up new possibilities that how you can write the algorithms for it, because the optimization algorithms, data factoring, prime number factoring algorithms, for example, they all exist, all have been written for the classical computers. But if we just talk about prime number factoring a very, very large prime number, which might be say 1,000 byte or digit prime number, it takes huge time, might take millions or zillions of years to get prime factors of a very large prime number. But with quantum algorithms written very thoughtfully, this can be done in few minutes as itself. Now, why exactly do we need thousands of qubits? We did talk about the quantum computing state right now with few qubits, but the research is on to bring as many qubits as possible. Why do we need that big a quantum computer? Because the quantum computing problem, as we said, is global. One operation that you're running, because all qubits are tangled, all qubits are entangled, one operation on one qubit or one operation on the quantum system state can perform huge change to the entire state and can solve your problem. So bigger the number of qubits, the bigger the problem that you can solve. So that is where the current hardware, quantum hardware industry is working for, to bring in as many qubits as possible. Now, just a small interesting fact actually. So 55, when we just saw that how exactly the amount of data being processed by, or equivalent amount of data being processed by quantum computer increases. So roughly 55 qubits is equivalent to 3 AWS snowmobiles. So you see on the right hand side, snowmobile is AWS storage or a device which can carry multiple petabytes of data. I mean, it's used normally to migrate data from your data center to cloud. So if you want to carry huge petabytes of data, so this kind of device, which is on a canter, is used. So 55 qubits of in a quantum system can represent information which is as big as 3 petabytes of, 100 petabytes, or rather 3 AWS snowball. Just an interesting factor. Now, coming to that thousands of qubits that we said. So this is the problem or the theoretical solution that people have thought of. If you want to break roughly an RSA 2048 So currently you need approximately 10 million qubits with expecting 0.1% error rate. So if you see large number of qubits as we achieve, we can solve huge problems within minutes, within seconds. So that is the target where in quantum computing industry is heading to. Now, what is the current state? So we did discuss what exactly is quantum computer, how it is working. Still, we are understanding the basics here. The challenge right now is we did understand that it is using quantum systems under it, and we are using supercomputing, we are using photonics and all those systems. But whatever hardware we are making or whatever qubits we are trying to create, they are not noise free. They are too much impacted by the coherence, decoherence or noise around that. So in typical bit scenario, if you want to flip a bit 0 to 1, 1 to 0, or if you want to make a phase flip, then the probability of phase error on these superconducting scenarios or the other scenarios is very high. So what happens is you have multiple qubits, you apply the operations on those qubits. It might happen that you get the errors here, then you apply more operations, then effectively the initial errors of these gates, then further errors of the other operations, they are impacted, they impact the output. Now, how to handle this thing? Typical scenario in the classical computers, if you see, when we transmit data from one system to other on the network, we usually get the error. And how we solved those things? We did error handling. We tried to bring in the redundancy in our network protocols so that the error checks or error corrections can be done on the other side. So if you taking the cue from the classical systems or classical networks, if data is transferred from one system to the other on the network, there are very high chances of noise, and what is being transmitted, there are chances that at the receiving end you get something else or distorted. So the classical protocols added error correction, error detection, all those mechanisms, and they added it with the help of redundancy. Exactly, so research right now is on towards two aspects: how to write the algorithms which cater to this kind of error detection and error correction. Also, at the same time, people are trying to increase the fidelity of the qubits or increase the performance of the qubits on the standard on the computing hardware that we have right now. Now, just taking an example, we said that we need 1 million or 10 million qubits to solve or break the RSA because Shor's algorithm in quantum computing system works on finding the factors of a large prime number. And if you see, the basic premise of a cryptographic algorithm is that you take a very large prime number whose factors cannot be found out easily on the classical computer, and then when you do the encryption, it takes millions of years. But on classical computer, if you see the Shor's algorithm, it might need 6,000 qubits to solve or find the right factors of a prime number. But these are all logical qubits. Now, what are logical qubits? These are all pure qubits, assuming there are no errors. Theoretically, if we take a theoretical scenario that there are no errors on the qubits, then with 6,000 qubits, noise-free qubits, you can break the RSA. But bringing in the error correction, considering the current noise level, bringing to find out the error detection and error correction, physically we might need 1 million qubits. So this is the current challenge or current area where we have where industry is working to. And that is where the current scenario is called NISQ, that means noisy intermediate scale quantum era, where we know that we are heading towards the right target, but we have not yet reached the final target. And we have to consider the scenario that yes, our qubits are with errors, and we should write the algorithms considering those errors. So this 6,000 Shor's algorithm on pure qubits is again yet to achieve. Theoretically, the algorithm achieves this, but because we do not have a quantum system with 6,000 qubits yet, so people are trying to write algorithms first considering noisy things, second considering the less number of qubits. Now, this is the current state, or this is how we are moving in the quantum ecosystem. In the classical computer, the error rate is very high. But in the quantum ecosystem on this, if you see, this is the error rate on a higher side. As you reduce on this axis, on the y-axis, error rate reduces. And as you move towards x-axis, more on x-axis, the number of qubits increase. So currently we are somewhere here where we have high error rate and our quantum computers have little less number of qubits. But as research goes on, and this is where people are actually fighting for the quantum supremacy as well, that whoever is achieving better error rate and whoever is achieving more number of qubits. But the end goal is that better number of qubits, must be there, higher number of qubits, and the qubits must be better with less errors. But currently, because this as quantum supremacy is being achieved, we are somewhere in between this second stage. And this second stage is called noisy intermediate scale, because we are right now in the middle of the this evolution, and we all know that the systems are noisy, so we should work accordingly. And this is the near term, because we have to build the application considering our challenges and considering what is available to us. So all thought process must go in this direction, considering the positives and the challenges both. Now, how things work next? We understood now that how quantum systems are working, what is their basics, what problems can we target. We'll go a bit more in detail in the concepts, but in the near term, how normally can they be leveraged for your application? So if you look at machine learning, I'm just taking an analogy here. In machine learning, what normally happens when you are trying to train a machine learning model, majorly you run your application on a CPU, and then to do all the optimization, all ML training, you pass your weights to GPU. The operations run on GPU, then objective function sends the information back. And because your machine learning training happens in multiple batches, so you do this iteration or epochs multiple times, and then you leverage GPU. So GPU becomes a co-processor. Considering the current state of QPU, again, same way, you can use CPU as your main processor, and then use QPU as your co-processor, and then pass on the parameters and get the results back, and do multiple iterations and leverage the quality and capacity of the quantum computer to solve your optimization problem. And also, if you see, in case you're building a application solution for your some enterprise solution for optimization, consider the logistics case, then you certainly would want to pass on the heavy lifting of the optimization from CPU to QPU, get the results back, and serve your end customers. So this is what is the current state or the right scenario to develop your applications on or do your research on. Now, this is what we understood so far on the hardware. I'll just, before getting into the further application level direction, I'll just take maybe 5 minutes to look at the questions that you have, and we'll try to answer them.
Yeah, so there has been some chat exchanges that have already been happening. I think one major question that came up is, are operating systems for quantum computers more complex than those for traditional or classical computers? And Anuj Malhotra already responded with a link saying that yes, they are more complex. And what I added was that because of error correction, the complexity is more. And today we do not have a scalable quantum computer, right? So that is there, but Sachin, if you want to add something, that will be great.
No, thanks. So Anuj answered, but from the application standpoint, rather than going too deep into the specific quantum computer and the operations on top of that, focusing more on the quantum computing or from the application standpoint, your focus majorly will be on building an application so that you can leverage the hybrid scenario, and consider a quantum computer as an external system offering you remote level of execution where I'm just trying to create an abstract picture here, that you build your application for the quantum computer and you remotely submit your code. Quantum computer executes that and returns back the code to you. Now, all the services and all the scenarios that are being tried to develop today, they are trying to give you all kind of abstractions from the hardcore quantum computer operating system and stuff. People are trying to create SDKs. For example, Braket SDK. You write your code in traditional or in the conventional Python with some Braket SDK and libraries. And finally, when you push the code, Braket SDK pushes your code to the quantum computer. and the code is executed and you get the output back. So rather than you logging into a quantum computer or getting the direct access, there are abstract layers being created for you from the application standpoint.
All right. So the next question is, with respect to the comparison with Snowball, can quantum computers store data like Snowball? I think there's some confusion here, but you might want to address that. Yeah.
Yeah. So that was just an interesting fact. Actually, I tried to share that how much processing or how much data can quantum computer process, or how much data can quantum computer state reflect. So that was just an idea. If you have 53 qubits or 55 qubits, sorry, then approximately it is equivalent to 100 petabyte of data being processed. So it's not like it's not a storage device. It's a processor, like we talked about CPU. It's a QPU, quantum processing unit, as we use the term. So you just pass on the information. There is a state being created inside the quantum system with multiple qubits, and when you pass on the instruction, that state is modified. So it's not storing the data. There is no storage device attached. Thanks. So when there are no questions, just coming back to sorry. Yep. So two technical directions. Now moving towards, we understood the underlying hardware concept in abstract terms. We did not go into the mathematics, how things are working. But just to with this concept of qubit, if we have to build a solution, or if we have to write some application on that, so there are two technical directions: the universal quantum gate and annealing. Universal quantum gate. Now, if you look at the left side, can you see my mouse pointer as well? I'm not able to. Okay, got it. Sorry. Yeah. So if you look at the classical computer, we did talk about the bits, and then we did talk about the gates, the AND gate, NAND gate, NOR gate, multiple gates that we talked about in the classical computer scenario. The operations happen on those bits, and finally you get the output. That means the state of those bits change, and you see that, okay, this is the output after these operations being performed. Now, universal gate approach on those quantum computers does the same thing. There are qubits, and then you are performing the operations. Now, where does the difference come? These bits actually carried 0 and 1, while the qubits carry a vector, a complete quantum state. Then you perform the operations. Certainly, the conventional operations were taking 2 bits and then giving the output again in the form of a bit. Here, these operations. Now, we did talk about vector. So certainly, these operations must be the vector operations. The other way of representing the vector state is in the form of, you can say, matrix. So these operations, you can say, are the matrices basically. So you can consider that, okay, this H is a matrix which is applied on this qubit. Then this H again is a matrix which is applied on this qubit. So you are performing those operations which are eventually the matrices, and your a complete calculation or the quantum state changes, and you get some new output, and you get a new state of the complete quantum system. So this is the universal gate approach. Just take an example. So poly-X gate, not going again in the details of what poly-X does, but poly-X actually reflects this matrix and the symbol, like we said. So if you apply this X gate on 0, that means a single qubit, which is this. So this will be just a typical matrix multiplication, and then you will get some output. And if you see X to 1, it is changing. So poly-X actually is inverting your one single bit or your vector basically from 1 to 0, 0 to 1. Similarly, you have multiple gates, poly-X, poly-Y, and poly-Z. But point is, there are multiple matrices which perform operation on the quantum gate, and you eventually end up having a new state. Now, you need to define your problem in the mathematics term, and then you continue to apply those mathematical or the vector or the matrix operations, and you get your solution out. So this is the mindset of a universal gate-based scenario. This is a screenshot from Wikipedia. Some gates and corresponding matrices that are being applied on your gates. Some of the matrices, if you see, For example, control not, they also have control bit. That means if it is following one qubit as the control qubit, that means if the value of the initial or the first qubit or the control qubit is a particular, it is one, for example, then this matrix will be applied to the second qubit. So some control units are there. So different kind of gates, different hardwares or different quantum computers support different gates. These are common gates, majorly supported by all hardwares. But then some quantum computers might support few additional gates, few gates differently. Then that is where a scenario like Braket comes in, where you can write your code in terms of Braket SDK or following the Braket SDK. So you can choose to write your code following the particular quantum computer's SDK. But in that case, you have followed one particular language, one particular syntax. If you want to port or you want to shift your code from one computer to the other, it becomes really difficult. While the layer, Braket layer, if you use a Braket SDK, if you have written the code in Braket SDK, then it's just about changing some configuration, some code lines, and you can switch your code from computer 1 to computer 2 easily without making any change. So those kind of layers or those kind of standardizations are being built up right now. Now, some additional information, just so how normally your circuit is defined. So this is your input and this is the output. The length or the number of gates on the horizontal, if you see, this is called the depth. And the number of qubits that you're using, this is called the width. These are the standard jargons for you to understand that this is how your circuit is defined. And then you can check the power of your circuit by multiplying the depth and the width. So this is a with 7 gates, this is the circuit. But if you look at the depth and if you look at the power of this circuit, it is 4 on this side and 3 on this side. So it is total 12. Now, we did understand about the circuit. Now, when you have written a circuit and you push it to a quantum computer for execution, you might also want to run this program or this circuit based on the change in input. Just take an example. If you are trying to do a machine learning training or optimization or some other kind of scenario on the quantum computer, your inputs might change. So you would want these circuits to take some inputs from outside or should have a feedback loop that changes the circuit behavior. So variational quantum circuits are just a variety where these circuits have few free parameters, and then they provide a feedback loop and can also take the inputs from the outside world, or these circuits behave on the inputs from the outside world. So this makes a quantum computer even more usable because you can define some circuits considering a class of problem. And when your data changes, when your scenario changes, these circuits can give you the output considering those data outputs. So if you look at a quantum neural network, it is just like a trainable quantum circuit with continuous parameters in. So you also have a feedback loop. So not going too much into the complexity here, but just giving an overall jargon view so that when you go and read about it, you should have a basic understanding that what variational part is adding to the quantum circuit. Now, coming to the second thread, we said there are 2 directions. So one direction was you can co-program your quantum computers using quantum gates, universal gate. Second set of approach to problem solving through quantum computers is through quantum annealing. Now, a different computer, most of the quantum computers that you have, IonQ, Rigetti, IBM, Google, all those follow the universal gate mechanism. There is only one computer called from the organization called D-Wave, which provides the annealing approach. So if you look at universal gate-based approach, they have quantum computers give you basic qubits and then they give you operations. You can build multiple complex operations on top of that.
Just a second, somebody who's just joined is on not on mute. Can you please go on? I'm trying to search who it is. Okay, I muted them. Go ahead.
Sure. Thank you. Thanks, Rina. Yeah. So second approach is annealing, as we said. In this approach, in the first quantum gate-based approach, it's a plain. I mean, you have full control where there are qubits, there are operations. You write your algorithm, you follow the operations, and you get the output. Second is a standard. I mean, we know that the optimization problems are quite common, and people try to solve those. So these qubits in these annealing systems are organized in the form of a topology or in some kind of arrangement. This arrangement actually is called a topology. Then you have to define your problem in such a way that can be mapped to those topology. We'll come to some more jargons, just keeping the information abstract for now. Now, once you have defined your problem, then this problem, if you have defined your problem in particular fashion, in particular kind of mathematical problem, you can map your problem to these kind of topologies. Then you need not worry about defining the algorithm. It's just like the operation, these the energy in these qubits or the operations on these qubits are performed in such a way that you get the output of your optimization problem. Now, another benefit that you get here is in a common, if you define an optimization problem, it's a very common thing that you are trying to find a minima or a maxima. That is how an optimization problem is defined. But in a bigger problem, in a bigger perception, there can be some local minima and local maxima. That means we know that the actual minimization that we are trying to find is this, but there is a minima here as well. So classical computers have been written with iterative or recursive or some other mechanisms to find out and not to be confused with the local minima, and they have to find out the global minima basically, or global maxima. Now, how classical computers work is when they reach when they find some kind of local minima, they have to recurse back and find out the global minima. These kind of challenges cause classical problems to last long and do many, many more calculations and take longer time. These kind of topologies in annealing and quantum systems allow a concept called tunneling. That means if you have reached a local minima, instead of following a longer path, you can leverage the quantum properties and some quantum calculations that we talked about, or those particular class of problems that we are talking about. Rather than going via this way, you can just simply found a tunnel and go to another, find another path and go this. That means many, many less number of iterations. So, and also because these problems have a single kind of solution, all fall back on a similar kind of solution. So mapping them to a single topology or single kind of arrangement makes the coding part much easier. That means once you have defined your problem, if you map it to the underlying topology of qubit, you will get the solution done rather than getting into hardcore gate-based complete algorithm writing. So the annealing systems are targeting majorly for the optimization problem only right now. So this is the second approach. Another intuition behind this annealing system is, say you have a local minima, you have a global minima, and then this is also one very local minima. The approach or the intuition behind this system is that you have set up some initial state, then you have set up an energy function which is passing on the energy, and then as you lower the temperature or as you try to map this energy thing, you can find out that, okay, in this entire topology, where actually you get the lowest point of energy, that is your global minima. That means a common optimization problem can be solved with this, passing on the energy to the entire qubit or topology structure that you have. And rather than going into multiple iterations like the classical computer, you just get this minimal minima very fast. So that is why we said that the concept of 100 years coming to few minutes actually. Now, this is an example we are saying in the one of the scenario, like, okay, this might be one scenario where how the qubits have been arranged, and you define this is a combination of 6 qubits. And then when you have hundreds of or thousands of qubits, then this structure becomes very complex. And how these qubits are connected, you need to understand the underlying topology. We'll see what topologies does D-Wave support. So D-Wave is the only system right now which is annealer. Rest all systems in industry that you see are following the gate-based approach. So now once you have defined the problem, you can just simply go and try to map, or the term used for this mapping is called embedding, that you have defined a problem. Now you embed this problem, mathematical problem, to the annealing based topology. What are the problems that can you solve? Just taking few examples. Protein folding, we all know, is a very common problem. People are trying to solve this problem with HPC, high performance compute, with large number of clusters. But if you see, it is all about finding the next minima or next, it's a typical optimization problem. And finally, finding the same tunneling impact, that local minima to the second local minima, and then finding the major global minima, is much faster with tunneling, actually, rather than going into a hardcore distributed cluster based approach where you are running the HPC problem for days together or months together. It can give you the results much faster. Another example, the use cases in the finance domain, there are lots of problems which require these kind of optimization. And the problems that we were talking about mathematically are called quadratic unconstrained binary optimization. We are going a bit more in jargons here, deliberately not going in the details that what type of problems are they, but setting up the context. In this case, to solve these kind of problems, you need to understand the Cubo formalism, that how to define your problem in the Cubo format, and then map it to the annealing topology, and then finally execute it. We'll see how it, if we'll see a small anatomy of this circuit when we go through a workbook. But this is how annealing works. So overall, we covered so far two different approaches. D-Wave is the system that is giving you annealing kind of setup. Rest all are giving you gate-based setup to solve the problems. So again, taking a logical break before we move further. So some problems that you have or questions?
I think most of the questions are getting answered by Anuj.
Sure. Thanks a lot, Anuj.
But there is one question in the local global minima maxima example.
Yeah.
Do we need to use a different algorithm too for quantum than the typical one for example gradient descent?
See, in the quantum system, if you are following the annealing approach, it is not about the gradient descent we are talking about. We are saying that we are trying again. Okay, if you want to take the minimization or optimization problem of the same gradient descent thing in quantum system, you have to formally map your problem to the Cubo. Just going slightly in the technical term here, in classical computers, we have problems with different time complexity. We do talk about polynomial time, P class problem, NP class problem, or NP hard, NP complete, all those kind of problems. So again, a Cubo belongs to the NP class of the problems, and you have to define your problem in a mathematical equation which falls back on the Cubo formalism. Once you have defined your problem, be it the gradient, gradient descent or some other optimization problem, then it is all about mapping it to the underlying topology. So thanks actually to Anuj. Actually, you have answered all the questions. Thank you very much. So moving next, so we understood how the hardwares are designed in an abstract way, how the algorithms or the solutions are being written. Now, what algorithms have been written? So if you see in this chart, what is the speed up potential? So this is the first generation algorithms on the quantum computer, which were written theoretically. So Shor's algorithm was written theoretically that it can solve, just giving some data points. Shor's algorithm is about finding the factors of a 2048 digit number. Classical computer based algorithm might take, say, millions or zillions of years to solve that. in worst case scenario. Shor's algorithm theoretically can solve that in few minutes only. But those are all theoretical solutions because we do not have pure qubits yet. Also, we do not have quantum computers with that many qubits with us. So these are all purebreds. And the second generation, when people found that, okay, quantum computers have matured with some noise and we can start writing. So people started writing the second generation of algorithms considering the noise and all other aspects. So these systems do not give the exponential growth, but yes, they do give the polynomial level speed up to the algorithms. And also in this scenario, the quantum computers have been considered to be the co-processors. Now, this is one example that we said. So this Shor's algorithm theoretically solves the problem in 6,000 logical qubits, while for considering the error correction and all those details, it covers roughly 1 million. It requires roughly 1 million physical qubits. Now, this is all very rigorous, but for the current scenario, we'll say that we must focus on this pragmatic approach where we are working with considering the quantum computers as co-processors and also trying to cover the noise aspect of the systems. Some of the algorithms, if you see the variational one, they follow the same approach. Annealing also falls under this bucket, basically. Now, these were some concepts to set up the basic knowledge level of the quantum computing. Now, what is AWS approach to quantum computing? We'll try to cover here. Now, AWS, we know as a cloud has a huge number of services, and these services are for typically compute, storage, databases we do talk about, but there is a service that focuses or that provides the quantum technologies access as well. Now, what benefits the service brings in along with the other ecosystems? First of all, the service name is Braket. The convention being follows is like in the quantum computers, we follow we define all the operations in bracket notation. Bra being a function, ket being a vector, not going again in the mathematical terms, but the service name has followed this nomenclature actually. Now, this is where Braket stands. There are multiple hardware providers. We did talk about IonQ, Rigetti, D-Wave. We'll cover those aspects. And then Braket lies on top of that. So you can program those computers directly using those hardware's SDK and other tooling system. But Braket lies on that, gives access to all three, D-Wave, IonQ, and Rigetti. It gives access to all three computers through one single SDK, one single interface. Second, it brings all these hardwares to the cloud ecosystem. So if you want to build some enterprise application, if you want to build some application, you need other services as well that we just saw. Common security thing, because you are processing your data. So security that you want, the SLAs, operational consistencies, technical support, all those things that you look in for a service, Braket brings to the quantum ecosystem as well. Plus a very easy to use developer environment. And then like you build your enterprise solution, other solutions on cloud, Braket enables leveraging quantum computers as the co-processors for your solutions. So cloud is also offering you compute, storage, APIs, databases, everything. When quantum computers come alongside, you can leverage, you can design your solutions on the cloud considering quantum computers as one of the components in the solution as well. Now, what different components are there? When you want to build something for the quantum computer, you need to write your code. Typically, people prefer to write in the notebooks. You can write full scripts as well. So it gives you managed notebooks. That means rather than setting up your quantum SDKs, Braket SDKs or other libraries, it gives you managed notebooks. That means when you start the notebooks, your development environment is ready. There are a large number of example algorithms to start with. So we did talk about Shor's algorithm. We did see Grover algorithm earlier, which is a search algorithm on the quantum. So all these implementations are available as reference in example. Many more are available. then rather than every time, I mean, you might write some code and then you can submit to the quantum computer to access or get the output done. Before actually doing that, you would want to try your code on the simulator. So you can run your code on different kind of simulators that can give you different level of performance for different circuits. Again, these are fully managed typical environment. You're not supposed to install or set up things like in cloud. When we say, just taking an analogy, if you are building a web server or web application, you can take a fully managed database rather than you installing the database and managing. You can have a fully managed simulator as well. You need not install, just write your code and say run it on simulator. It will run there without you worrying about setting up, configuring all those things. Then finally, multiple quantum computers. We did talk about 3, we'll cover there. Finally, when you're building an application, you need to monitor the performance, progress, other things as well. So you can do that as well in the cloud scenario. Just taking an example, if you're building a web application, you would want to monitor the performance or other aspects of your web server or database. So all the logs are pushed to the service called CloudWatch, Amazon CloudWatch. Exactly same way, when you're using a service Braket, all the logs are pushed to the CloudWatch. So Braket brings in quantum computing to the main stream, so that you can leverage this service as you're leveraging the other services of the cloud. Now, this is the architecture on a high level. So Braket is service. How you can access? You can use the managed notebooks. Like we said, you can create the notebooks in cloud with all the environments preset. You can choose to download Braket SDK, set up on your local environment, laptop, or maybe directly go to the Braket console and start working. So you can connect to the Braket service through the SDK. Go to the simulators or leverage different hardwares, but Braket service is integral part of the other cloud services. So CloudWatch, like I said, for managing the logs. In case you want to access the storage, so another service. This is just an indicative list. There are other services, many more services as well. So S3 is the storage service, object storage service, in case you want to access some storage. For managing the permission. So the way you manage permissions at a very granular level for your other setups, be it your machine learning setup, be it your database, be it your analytics or IoT or any other setup, same IAM service you can use to configure the permission on the Braket. And then in case you want further security, because your data is there, you want to encrypt the data. So a key management service is also integrated. So Braket can be leveraged to build this solution that meet your security requirements as well. Now, these are 3 systems that we talked about. IonQ and Rigetti are provide the universal gate-based approach, and D-Wave provides annealing approach. IonQ follows the underlying hardware, which is ion trapping. Rigetti follows superconducting, and D-Wave again also follows superconducting but gives the annealing environment. Now, D-Wave, like we said, annealing, and this is all typical qubits approach, like we said. Some configurations or some simulators. So 3 simulators, we said, it supports 34 qubits to simulate. See, we did talk about a huge data or RAM requirement, because the qubit state or quantum state of a system processes huge amount of data. It is extremely difficult to simulate on a classical computer. But these systems, if you see, they can provide up to 34, 50 or 17 qubit system state. So that means the RAM requirement, if you see, it is like 2 raised to power 34 minimum, 2 raised to power 50 minimum, and accordingly. But you need not worry about this case. You can just submit your requirement. You can submit your job, and Braket as a fully managed service takes care of it. Other than that, it also provides 2 local simulators. So these are all cloud-based simulator. These 2 simulators are local. That means part of the Braket SDK itself. That means if you are setting up Braket SDK, maybe on your managed notebook, like we said, or maybe on your own laptop, you can leverage the simulator on the local machine wherever you have set up Braket to simulate your circuits there itself. So before you reach to the final quantum system, you can try to write your code on the local simulator itself, verify circuits are good or not. Then maybe as a next step, you can push it to any of the cloud-based simulator to test your performance, and then finally reach out to the quantum system. Now, all this setup in a fully managed scenario makes using quantum systems much easier. And this is any queries so far? I mean, I'll just check the questions. We'll take a logical break actually here again.
Hi, there are like currently 2 questions, so I can read it. I can read out those 2.
Yeah.
So one is from Janani, I guess, and she's asking, is there any restriction on accessing hybrid solvers of D-Wave from AWS Braket?
No, so when you say D-Wave solvers, Cubo solvers or the other solvers, you can, I mean, there are ways to access those solvers. There is no restriction as such.
Okay. And so another one is from Satya, and he's asking IBM Qiskit based tab and notebook. So can we bring here and do?
See, IBM, I mean, the IBM Qiskit based notebook will be using the IBM's own SDK basically. Also, Braket actually gives 2 points here. Actually, Braket gives the interface for these 3 systems that we are talking about. The D-Wave, Rigetti, and IonQ. IBM follows the gate base, so not talking about D-Wave here. You will have to write your code in the Braket SDK to run on the Rigetti or IonQ here. You will have to work to change your gates and all scenarios that match the Braket SDK scenario.
Okay. Thank you so much. So we have another question also. So do local simulators are available on AWS Outpost? It's by Nilesh.
Yeah. So when we say that you can set up the Braket SDK on your local environment, so that local environment can be anything. It can be your local laptop, it can be your local server, or it can be an AWS compute service EC2 as well. Outposts offer EC2, so I mean, it's a typical Linux machine. Yes, you can set there.
Yeah. Okay. Thank you. So these are all.
Yeah. So just moving a bit further. So we did talk about the hybrid ecosystem. Now, how Braket brings in the hybrid scenario. So far, we said that Braket SDK lets you submit your jobs to the quantum computers or simulator. But in the hybrid scenario, you would want CPU and QPU to work together. So Braket also offers hybrid jobs. That means you can write your jobs considering that considering a standard application, and that application making intermittent calls to the QPUs. And you can submit your jobs to the Braket jobs, which will run on a classical CPU. When this classical application is running, any access to the quantum circuit on the simulator or on the hardware will be pushed from this job to the QPU, and then this loop runs. Going a bit more on the technical side here, consider just like there is a container and you are submitting a job in the container. So a container is running here with Braket SDK and a few more libraries of your choice that you can set up. And then within that, in that container, you have your own script, your own algorithm working, classical execution using the Braket. And within that algorithm, with the Braket SDK, you can pass on the make the calls to the quantum system as well. So Braket jobs are a complete hybrid scenario. Second point, just take a machine learning scenario, some other scenario. Normally, when you are submitting a job to a quantum computer, there is a job queue. You submit the job. When your job turn comes, it is executed and you get the output back. Now, when you are running this kind of job or a loop scenario, if you submit first job, then you get the output back. Second job, when you submit, it goes into the queue again. That means your job will be waiting for a longer period of time. Hybrid jobs prioritize your submission to the quantum system. That means when you submitted the job 1 or task 1, in the iteration when the task 2 comes, it is prioritized and is executed faster. It is given priority over the regular queue basically. So you do not need, your job or task need not wait long in the queue to get the quantum system's time. So that benefit also comes there. So these are some conventions. Now one thing we did talk about the noise in the quantum system. So normally when you are executing a task, so this is any circuit execution on a quantum system is a task. So same for the Braket as well. Now when you are submitting a task, we all know that when this circuit is executed, the output might not be right. Of course, we are taking care of the error correction and all those things, but still you would want to increase the fidelity. So you would want to run the same circuit multiple times. So each execution of a circuit is called a shot. When you submit a task, you specify that, okay, you run the circuit maybe say 100 times. Now, the circuit is executed 100 times, means 100 shots of a single task. 100 executions will give you 100 outputs. That eventually becomes a probabilistic, so that eventually becomes a distribution. And then you take the output, expected output of that distribution to take to the next step. So this is the relationship of task and shot. Now the job, like we said, you are submitting a job which requires multiple iterations. Every iteration will be a task. So hybrid job ensures that the tasks are prioritized. So task goes into the queue, executed. When it is executed, the number of shots will be executed in a single run only. But you want to run multiple epochs, so those epochs will be submitted like multiple tasks there. So these are the jargons and how they relate basically. Now, the same thing, like we said, we covered already. So a job instance is just like a container. You submit your algorithm, it will run the regular on a classical CPU. You can make call to the simulators, you can make call to the quantum processors, and you can leverage the storage, you can leverage other cloud services as well. ECR is a elastic container service. You might want to create multiple containers with your own libraries, with your own algorithms. So you can create your container, you can put in your own container registry, in AWS container registry, and every time a job is brought up, it will bring the container image. The classical container scenario that you have for your web application, for your other scenarios, can be leveraged with the quantum computing jobs on the Braket. Some more things to bring quantum computing to the mainstream. If you are building any classical application, you log into the system. Say you have created a web page and you log in. So you are authenticated that, okay, you are authorized to access this API, or you're authorized to access this feature, all those things. So those user level management is done. There is a user management system or subsystem in every application that you build. You might want to build that thing in around quantum computing as well. You might want to bring some microservices like architecture or some API kind of subsystem in front of the quantum computer. So Amazon's API gateway service, along with the user management service like Cognito, can be leveraged with Braket to bring in the conventional REST API or all the other APIs that you talk about along with the Braket. In case you want to use the container in other compute service or some with some other service, that can those integrations can also be brought in. In another example of bringing the quantum computing in the mainstream, you want to make an event-driven system. We always say that, okay, some notification is generated, some information is stored in the database, some analytics is done. So Braket is connected with Event Bridge, and from there you can connect to all, you can leverage in your design the database, machine learning, all other services. That means Braket comes as a mainstream in the cloud. One final point before we go on the queries again. We did talk about the gate-based approach. We did talk about the annealing approach. Quantum Braket is also integrated with Annealing, which is an ML tooling for quantum, which supports, which is in machine learning, you are doing differentiation or automatic differentiation of the mathematical equations that you're doing for machine learning. Annealing allows automatic differentiation of the quantum circuits, and it is very well integrated with TensorFlow, PyTorch, all other ecosystem. That means if you want to do quantum machine learning, Braket is integrated with Annealing. On the Braket examples, there are large number of examples to do machine learning with Braket or with quantum systems. So before we go into the closure side, some queries that are left actually.
Yeah, we have one question from Vaishnavi. She's asking for some kind of study material that is based on this, like today's session.
Yeah, I'll show that. I mean, I'll show those links.
Okay, okay.
I'll
Sure.
give a walkthrough of the Braket as well. We'll give some walkthrough of the code as well to give you comfort actually. You will not be writing the code, but I'll give you some context that how what we are saying, how it has been converted to code basically.
Okay, okay. Okay. Yeah, that's all for now.
Yeah. So one last point. Braket, Braket has a huge community of researchers, application specialists, tooling developers, all those things, people coming together and using Braket and doing stuff on the quantum system there. Now, we did understand about the quantum ecosystem. We did understand about what Braket is offering there. But point is, considering the current state of the quantum computing, why you should engage now. So are there any business applications already being used? I'll say at least I'm not aware of any production grade application, but we saw that this system or this quantum ecosystem going to bring a big change. So engaging early is always good. As you engage early, you will get to develop new algorithms, and you will get to develop new IPs. You will get to learn fast and see how technology evolves, and you will be early one to get the benefit of those calculations and scenarios. Now, how it fits in, if you see typically in innovation flywheel, how it happens, there are customer experiences, there are use cases and algorithms. As they with the customer experience, you build more use cases and algorithms, you invest more in the quantum, and then you finally get more machines. So this is a system that continues to grow, and finally it's up to you which system do you want to be part of. So if you see in Braket scenario and in other quantum computing scenario, these are the organizations fitting up in different areas. So I'll just go back. If you see people building high performance machines, people building customer experience around cloud scenario, you can choose your interest area and spend time in learning those areas as well. It's really difficult to go and learn all the aspects, but you can choose one area, spend time there, and build your expertise in that particular area. So if you see, these are the organizations which are building different ecosystems or different areas of this entire quantum computing growth in a scenario. So you can choose which part of this entire growth ecosystem you want to be, which maps with your own thought process or learning inclination, and accordingly you can go and choose. And how do you want to build the expertise, and what approach should you take? First is like you can start with a small POC. I mean, first go for some training, some sessions, some videos. I'll share some links with you. Then try to do some level of POCs to build the concept. Once POCs are done, maybe from the past experiences, from the past examples, then try to bring those POCs close to the use case that you understand that in your ecosystem. Then gradually build up on those use cases and try to solve those problems. And finally, keep on, I mean, the iteration and working through the classical, I mean, the pre-solved examples and iteratively building on top of that is the right way. And finally, because there are very less number of algorithms right now, but yes, as you go build and solve some problems, you might end up in some IP or all those things. So this was from the concept or theoretical standpoint before we go to the Braket's console and see things there. So any queries if you have before we go to the final?
Yeah. There is one question. So Manoj is asking, like, is AWS providing any certification opportunity for Braket?
Quantum, I mean, we just saw that it's such a early stage area. It's very difficult to give any certification or justify the knowledge there. So as such, there is no
Okay.
certification in Braket.
Yeah, and there is another question. So can we get Sandbox account to try out ourselves? Sandbox. Yeah.
We can connect actually sometime to understand what kind of problem you have and see that how we can help you. Now, it's difficult to answer this question now, but we can understand the problem and see how we can help you there.
Okay. So it's not possible for ourselves to try.
No, we can discuss on the
Okay,
opportunity, like what problem you are trying to solve, at what stage are you, and how we can support you. We can discuss on this. But there is no general public sandbox available where everyone can go and log in.
Okay. Thank
And
you.
if I may add, I think one of the things that we were discussing, Sachin, was that if there are enough people with certain problem statements and who are willing to go through later, a one full day kind of a session, maybe, people should send, if there are more people interested in something like this and they have problem statements that they want to tackle, then sending an email back saying that, and that helps us understand whether there is a need for a more detailed session later or not.
Sure, we can do that. And there we can bring in some maybe accounts, we can arrange for some accounts, we can take internal approval, and then we can give some kind of hands-on experience as well.
Yeah, that's what. So I think that is the same account that people can use for the hands-on experience, and maybe it could be extended for few days or something like that. So
we can,
yeah. So please, I think this is a request for everybody to think about any problem statements you want to address and try on, and send an email back to the email ID from which you got the invite, and keep Sachin and myself in the loop, right? Yeah. Thank you. Thanks, Sachin. Yeah.
sure, thanks. So thanks. So this was all the concept building. I'll just move on to the Braket console to show some demo once, so that you get some idea that what we were talking about and how it is converting to the code. So this is the AWS console that you have. Some of you who do not have any experience with the AWS console or the cloud console before, this is the main console. And we did talk about large number of AWS services. So all these services you can see listed here, like if you want to see compute, containers, database, all those services. So alongside you will see the service like quantum technology here. And when you click here, you will see the service in this particular category. So these are the categories. And then under those categories, you see the different services. Also, you can search easily from here for the service if this list is little exhaustive. So when you click on this Braket, you access the Braket console. So every service has its own console. So you access this console. On the right hand side, if you see on top, AWS cloud has multiple geographical regions across globe. So quantum computing service Braket is available in 3 regions. So you can see, and these systems that we talked about, these quantum computers are available in different regions. We'll cover that. So this is the Braket console. On the console, when you see on the left hand side devices, so this gives you a list of all the devices that are available to you. So we did talk about the Annealer devices, D-Wave. So 2 D-Wave devices. It also mentions the details. These are Annealer devices. The underlying is superconducting qubits. How many qubits does it support? The status, and right now it is available. In case you want to submit the code, it will be executed on this quantum computer. Also, it tells that which geographical region it is in. So it is in US West 2. So if we go here, so US West 2 is Oregon. So it is this system is in Oregon. IonQ, it supports 11 qubits. It is a universal gate-based model and follows the trapped ion. it is in US East 1, but this system is online, no issues, but it is not available right now because the few systems actually are available only for few hours a day, because these are really rare systems. So some time slot is allocated. So what happens in case you submit your job right now for this INQ, it will go in a queue. As soon as system becomes available, that job queue will be cleared by executing on that INQ system. So it will be available in another 3 hours or so. Similarly, Rigetti has two systems here. Just sharing this, Aspen 11 actually is an older system. It will be phased out by the end of February. Aspen M1 is the newer one. It has just been added. So also, in case you want to see the older systems which have retired over a period of time, so if you just turn it on, if you will see that large number of DWave's older system, this 1.1 is retired. So many systems you will see which are retired, you will see their status marks. So you can see what, how things have changed. If you see, Rigetti started with Aspen 8, it had 31 qubits. Now it has reached to 38 qubits. And with Aspen M1, the number of qubits have increased. So all those things, all the status you can see here. Then as you go down, we did talk about 3 simulators on the cloud. They're all information of the region, their availability, all those things are mentioned. And any changes that might happen in their schedule, that might happen in their availability, all announcements you will be able to see from here easily. So we said that new QPU added, so it's announced here. So all information is available to you on the Braket dashboard or console itself. Now, this is these are the devices we said. In case you want to go and get more information about them, you can click on this and you will get a special separate page for these devices. Yeah, and some more information. And in case you want to go to the device's own website, you can go there. Now, we did talk about the managed environment. So this is the managed notebook. You can create your own notebook. I'll just create one. It might take 2-3 minutes or 5 minutes to create, but I have already one notebook readily available. So I'll just create one in front of you, but we'll go to this notebook because it is already live. So if you want to create your own notebook scenario, if you want to set it up on your local scenario, then there is a documentation page where which tells that how you can download Braket SDK and set that up. But in case you want a ready scenario with all those things, just go to create notebook, give a name here. You choose the size of the instance or size of the machine. For example, T3 medium will have 2 vCPUs and then 4 GB RAM. So accordingly, you can choose. We normally recommend that you choose a smaller size, because when you're writing the code, when you're building something, you do not need a bigger server to do the task. So you can choose a smaller machine. Normally, you have a 5 GB space already available, which more or less is sufficient to do all your development work. But in case you want to increase the volume, permission settings right now are not going in detail, but on a high level, in AWS, the security is job 0. By default, when you start accessing AWS, it's a very conservative policy that you do not have any permission. If you want to access, we did talk about accessing the storage, for example, the S3 service, the S3 storage service, or the data on the S3 service, you need to have permissions to read that. So you need to give the permission to this service as well, or to Braket service. So this role that has, we have already created for when you access, you will have to create one role giving permission to the Braket to access the storage. And then in case you want to go for the encryption, you choose the encryption key. Network settings, not going in detail, but we said that Braket is part of the cloud ecosystem. So all permissions for accessing the network level permissions for accessing the notebooks and all those you can configure from the network settings here. Then just saying create notebook instance. So it might take say 5 or 7 minutes, it might come up, but your environment will be ready and you will get a link here. I'll just start one environment here to showcase. But before getting into this, we did say we did talk about jobs, tasks, and shots. So if we go to jobs right now, we may not have a job in this account which I am sharing. So all the jobs that you are running, all the jobs that you are running, they will be listed here. Where have these jobs been run? So this is the scenario or the ID of the device. it has been run on a quantum simulator, and this was an SV1 simulator. If we just go here, so we have 3 simulators, SV1. If you go in detail to the SV1, see, this is the device's ID, and the name also tells. So if you see, this job has been run on this particular device or this particular simulator, SV1. If you want to go further in detail, all listings, all things are maintained here. A huge detail where exactly the script was, because we said that you can create a script and then you can pass it on. You can create, I mean, all advanced things, like you can create the checkpoint. What was the underlying instance for this job? How much time did it take to run? All those things, monitoring, all those things are mentioned here. In the job, you can have multiple tasks. So what tasks were there? You can find the list here. The logs and other things, we said integration, everything here. And these are the tasks that we submitted. You can submit an independent task, or maybe your job submits the task. Most likely these all tasks were submitted by that job only, but in case you want to go and see information of each and every execution. So yes, this was the job. It executed 100 shots. And this is the S3 bucket that was used for storing the output. So all information remains there even after you have executed your tasks there. So this is the job listing. This is the task listing. But what it is showing right now is for the North Virginia. If you go to jobs and if you change your region, if there are no jobs in North Virginia, in North California, or the other regions, it will not show. So it is region specific. So it might not show anything if no job was run in the California. See. So this is the overall setup that we talked about. Going to the notebook now. I'll just start the notebook that already existed. So this is the management. So if you see, it will take hardly 5-7 minutes or so before this ready environment comes up without you worrying about installing anything. And you will get a full Jupyter notebook environment to start with. So this is available. Braket examples are already there. There is a GitHub link also for these Braket examples. But if you go in these Braket examples, you have large number of examples. So getting started tells all about the basic systems, how code is written on the Braket and how it can be executed on simulators, how it can be executed on the quantum systems. You want to write the hybrid jobs, hybrid algorithms, advanced circuit algorithms. If you want to see the Grover algorithm and search algorithm, and if you want to see Shor's algorithm, you will also find in view in some code there. Also, the annealing system and how machine learning is done with penny lane. So all those examples are available for you to start and do. I'll just give you example. Give you a walkthrough of 2 examples here. So just starting with annealing, there is a D-wave anatomy. I'm starting. I mean, just to give an idea that how exactly things work on an annealer. You may not follow all the things. So I'll also try to keep all the things very abstract, but you will get the idea. You will be able to map it with what we talked about. So if you remember in the annealing, we did talk about defining a problem mathematically and then mapping it to the underlying system. D-wave has, I'll just go back to the Braket once. So D-wave has 2 systems, 2000 and the advantage system. If we just go to their pages, these 2 systems. So this system has 2048 qubits and this system has 5760 qubits. Because of this strength of the qubit or this large amount of qubits, and their topology has been defined differently. So this 2000 system follows the chimera topology, and the advantage system follows the Pegasus topology. Now, whichever system you choose, you will have to provide the mapping of those qubits, that problem onto the topology. So if you go, not going in again the mathematical terms here, but just point is you are defining your system or problem in the Cubo format. and then you are embedding, that means your map, you have defined your problem in an equation, quantum quadratic unconstrained binary optimization. That means some optimization problem, but in the in a binary optimization way. Once you have defined this problem, this is the formulation that you have to do outside your code. Once you have done this, then you just need to write the code to define this kind of structure and just embed it onto the DWave system here. So here what we are doing is, if you see, we'll not go too much in the code because we understand that we have just learned the concept, so they might become little heavier. But if you see, we have just imported the AWS device thing because we will be using AWS device identifier to run things on. Then some classes or some information for running the code on the Braket on DWave. Common, just running. Just importing some libraries. So this network X library will help us create a network basically, and then we will create a random network and we'll just try to map it to the DWave. So here I'm just defining some bucket name. I'll have to go. So guys, any queries so far? Because this might be a little tough because you're seeing it for the first time. So you may or may not follow all the things that we are talking now.
Yeah, currently I don't see any queries in the chat regarding this.
Just using okay, so create one. Sorry, I don't have. So just define the storage where all the Braket output will be kept, because we'll be accessing the SD. We have already given the permission. Now, if you see, this is AWS device that we are going to use. We are going to run our code on DWave. So if you see, if you just go and check DWave 2000's ID, so it is the same ID that we are passing. So it's just like we are telling which device to use, and that's all. Rest all DWave Braket SDK or Braket system will automatically take care of. In case you want to just switch from DWave's 2Q system to the Advantage system, just the ID changes and rest all remains same. So it's the device variable that carries the information, and you will be running it further. So I'm just commenting it for now to run it on DWave. This is just giving you the information that which device we are talking about, in case you want to fetch the information of the device from the code. So it's a standard ecosystem available, that you have a device and you have asked for the properties of the device. So it is giving you like, okay, it carries these many physical qubits and other couplers, and how many shots can you run. So 2000 DWave 2000 device allows you to run the shots in the range of 1 to 10,000. So you can run up to 10,000 shots. So in case you want to see on the other device, sorry. So this is the number of qubits in the Advantage system, and the couplers increased. Now, this is what we talked about. So Pegasus graph, as we are saying, on the so this is the chimera topology that we talked about on the DWave. it follows this kind of structure. Not again going that why are they following this and what benefits do you get, but just giving an overall scenario. The two systems giving two different types of topologies. The 2000Q gives the chimera topology. And the other system, the second system, the advantage system gives you the Pegasus topology to Pegasus topology. And if you see the connectivity structure of the chimera graph, so this is how the topology is. So if you see multiple qubits, they have been joined in this fashion. One set of structure is created, second set of structure is created. So here if you see, then to join these two sets, 4 connections have been given. Now this entire ecosystem gives you a complete quantum state, but for annealing, you need not go and program for each system. You can just define your Cubo problem and just map it or embed it onto the topology there or the system there. So if you just define 2 by 2, so exactly same system, but the connections change. If you go and make it 3 by 3, the structure, it will show you that how chimera topology has been defined. And the Pegasus is a little complex. It supports up to 5,760 qubits. Now, if you go further, we are just trying to take any random graph, complete graph. Complete graph means each node is connected to each other node. So we have just taken a complete graph with 9 nodes here. It is giving us randomly. So if you run this code again, a different kind of formation might come up. Now, what we are doing here is we have taken one topology or connectivity structure for 2 by 2 and just simply using the internal function of Braket to find the embedding of this graph on the connectivity structure that we have. So this is, so we took the object of D-wave network structure of the chimera, then just trying to find the embedding. We have already defined this graph structure. We have defined in the Cubo format. We have taken the random one, but for you will have to define your graph because quantum unconstrained binary optimization means you have a structure like nodes and edges, and your problem will have a different kind of node structure with different connectivity. Just take a traveling salesman problem. It's a Cubo problem basically, or maybe shortest route problem. That is also a kind of a node and edge problem. So eventually you will get a graph, and then from once you have defined your problem or equation that maps to the graph that you're talking about, you can simply find the embedding. It tells you that how these 9 nodes have been connected. Even the graph coloring example, if you say, and find when you execute this code in the embed, I'll just take it. Yeah. So if you see, we have defined one Cubo problem here. So we have taken the random graph, but now Cubo means our quadratic unconstrained problem in the equation format that is just going up. Yeah. So the constant, the variable, constant and the variable. So, and the minimization or the maximization problem, we define an equation. So in the Cubo problem, we are just passing on these nodes, these constants, these variables in the Cubo format. Just one. So here we are passing on that quadratic equation, and just finally taking this simulated annealing the sampler or the code from, I'm not deliberately going in hardcore explanation of the code, but just mapping it this problem to the underlying system and then executing or pushing it to the pushing it to run on the D-wave system. So on a high level, just wanted to pass on the message that define a problem in the Cubo form, find the right embedding and push the execution on the D-wave. So this is the overall structure. Not going in line by line explanation because I feel it will be too heavy in the first case. But yes, as we go along, in case you want deep dive session, then we can try to work for an immersion day kind of session where we work on each and every instruction, explaining each and every problem there. So this is annealing. Any queries so far? I'll just give us a high level walkthrough of building a gate-based system also.
Yes, we have several questions now. So one is from Nirmal, and he's asking, how do we access D-Wave hybrid solver through Braket?
See, for accessing D-Wave solver, D-Wave has its own, I mean, you'll have to set up some additional libraries. But because Braket is part of the cloud ecosystem and you can configure the network structure and all, you'll have to set up some additional libraries on this notebook to push your job to the D-Wave solver.
Okay. So we have another question, but it has been answered by Anuj, but I'll anyway read. So he's asking, I think you are hinting at a real time. No. The question is, can a video analytics and processing application running on AWS GPU instance can be executed on QPU instance and check for performance? So in case possible, can you suggest the process?
So when you say a video analytics and processing application, what I mean, not clearly understanding that what kind of analytics you're talking about. So again, breaking down into two aspects, or maybe if you can provide some more information that what level of analytics are you talking about here?
So it's not like explained by Mr. Subhendu, but Mr. Anuj has answered the question. Hello, can you hear the question?
If you can type, actually, if you can type, it will be easier. I'm not able to hear what you're saying. There is some noise coming in.
Yeah, even I'm not sure who's. Okay, yeah, it's solved now. So we have another question. So is it possible to put in a feedback loop into the Q circuit and try to compute a predictive futuristic state after n number of most probable actions identified to be executed in sequence, identified as the predictive output per shot, but then feedback into the circuit for next computation?
Yes, you can do that with hybrid job. So hybrid job actually is providing you that loop there. Yes, you can do that. I mean, it's up to you how you define your job, how you take the input from the previous circuit and pass it on to the next push of the job. Yes, hybrid jobs, you can leverage that. And that is where the variational circuits will come in.
Hi, Sachin. This is Shubhendu here. I put that queries regarding video analytics. So should I elaborate you on that one?
Yeah, if you can, I mean, yeah, share more. I think the questions were answered also. I mean, I'm not following, I mean, I'm not following the full chat. Shubhendu, not able to hear you. In case you can explain, maybe in the chat, we'll be able to answer it.
Yeah, I don't see any questions in the chat now. So
I was muted again. So the question, the thing here is that if taking a real stream feed from a camera and inside a GPU instance, I am running a model that is constantly understanding that stream and then doing the next phase of analysis. If that particular thing is currently running on a GPU instance, so can I just host it on a QPU instance and check for some improvement in performance?
Yes. So you are talking about ML inference basically. Can you please go on mute? Yeah. So you are talking about ML inference on some system. See, theoretically, yes. But practically, if you see two aspects, you need to check actually how much performance are you getting. Second, you just saw that quantum systems are really scarce and you have very limited slot in your daily time available to you. So first, breaking into two aspects. One, can there be an algorithm? Yes, theoretically, yes, but does it exist? I'm not sure. Because people are doing multiple machine learning kind of scenarios, multiple optimization level execution, so it should also be possible. But can it be done in the production scenario right now? Not sure on the quality of that algorithm. Second, the systems are available only for a very short period of time, so bringing it into the real time, not sure. Also, if you see all things that you're running, they're all job based right now. So you submit a job. So when it's coming into the real time scenario, you might take a packet, you have an algorithm, assuming you also have an algorithm, it might not give you a real-time return back. You will be submitting your video or data in a bad job scenario. Output will become.
I hope this was not interesting.
Can you? Yeah. So, considering the current ecosystem, I'm not sure it will be possible or not.
I can't hear you, Sachin. I don't know if others can hear you. Sachin, I think people can't hear you.
Oh, maybe, yeah. Can you hear me now?
Yes, yes.
Maybe there was some background noise, so somebody, the host would have, or the master would have muted me basically.
So if that previous question is answered, we have another question. So, it's from VK, and he's asking, do you have any predefined architectures for specific use cases that we can take a look at in terms of integrating AWS Braket with other regular AWS services?
Yeah, so if you go here, I'll just show you. So if you go in this Braket this folder, so you will find the examples of the hybrid jobs. That hybrid jobs, tasks are things that you can execute purely on the quantum computers, but jobs allow you to run full-fledged solution, which and also Braket jobs have classical CPU integration where you get the container environment. So here you can see the examples of bring your own container, hybrid parameter tuning, all those examples you have here. And when we say bring your own container, basically you are executing a classical computer's code on the Braket jobs. And wherever you have AWS examples, large number of AWS examples across internet, you can choose to use any of them to connect to other AWS services. So it's just like if you want to connect to any other AWS service, or you want to leverage those services through programming, there is an SDK called Boto in Python. In fact, AWS has SDK in multiple languages. You want to use Java, .NET, any other, so you can choose your own language there.
Okay, thank you.
Yeah, but for Braket jobs, most likely you will be using Python, because Braket SDK follows Python language to submit your jobs on the on quantum computers or simulators. So you can choose to use Boto 3, which is the Python SDK. And you can connect to any AWS service.
Okay. Thank you.
Yeah. And just taking one more, just going to getting started actually to show that how systems can be run on the simulators, or how systems can be run on the devices. So just giving a walkthrough. So not making any change in the scenario. So if you see, this kind of circuit is being created. Or rather, just let me give you an example from this getting started first. So how circuits exactly are being created? If you see now some libraries being introduced, and if you see the circuit class actually lets you create the circuits. Now, another good point here is, see, every device will have some or the other gates or the operations possible. Braket also has a large number of gates possible. Braket will automatically parse the gates or the circuit that you have created and will map it to the target device. So for you, you need not worry. You can just simply work on the gate definition that Braket has given, and then it will automatically map to the right gate in case some gate is not available on the target system. So Braket will do that mapping, that how Braket's gate will map to the single or multiple gate structure on the target device. You need not worry about that. So this is just kind of a bell state being created. And when you say where to run it, it is the local simulator. That means the job will not be submitted to the cloud simulator. And finally, you simply say, okay, device run, and this is the circuit. So if you see, you have created a circuit, you have taken a simulator and you have run it. So this is a bare minimum that we see. And then the output that we talk about. Now, if we just simply move and follow this convention here, the circuit has been created. Some multiple knots have been added to the circuit, and then finally this complex circuit has been created, and then you chose local simulator and you execute it. Now, if everything remains same, you just go and change the device. Just one. This is yeah. You just simply change the device, same circuit being created, and it executes. So if you see, everything remains same, only the device changes and your circuit changes. And circuit creation, we just saw that you keep on adding the circuit through the convention that we are following here. Different circuits that Braket has. If you want to run this circuit on the quantum computer, I'll just go here and we'll check this example. Everything remaining same, there will be a device change. That's all. So if you go and see, it's this time it is this device and this device, and what gates actually are supported by various devices, they are mentioned. If the Braket supports those gates, they'll be mapped directly to the gate under. Otherwise, you can follow. It will convert your gate. It will automatically convert Braket's gate to the target device's gate. So only thing changes here is the device name, and you can run your circuit on different devices. So it's very similar to the low level or the assembly level programming that you did in the classical computers. But yes, the thought process changes because here we do not have bits, we have qubits, and the operations are not bitwise. They are the linear or the advanced operations that we have. So this is the overall, I'll say, first level setup that we had. If you have any query, then we can answer. I mean, we did plan this session for the longer, but I think we are able to cover it faster, I guess.
Oh yeah, there are no questions currently.
So if you guys want to have maybe a deep dive hands-on session where we explain each and every instruction, some maths, so we can work on that part. So over to you, Reena, actually. So Reena, we did plan for 3 hours, but I think we covered a bit faster.
That's good. I think we can look for, if people have questions, I think this is an opportunity to ask both kind of questions, questions related to the content, any other doubts around Amazon Braket, or any questions around quantum in general. Also, if there are any questions related to logistics, about QETCI, etc., we can address those as well. So I would request people to raise their hands if they have questions, and we can, sort of unmute them and they can ask. Actually, participants can unmute themselves. So yeah, just raise your hand if you have a question. So the question, I think, from Vishwa Tosh is, can we have sessions on quantum cryptography? Sure. I think it's a very, very relevant topic. And right now, what we're doing is we're doing industry sessions. So we have the next 2 sessions lined up, focused on the Microsoft and the Google stack, but we will include quantum cryptography as well. So that's a good point. Yeah. Vadim Khan has raised hand. Please go ahead and speak, Nadeem.
Hello, thank you, ma'am.
Yes.
Can I ask?
Yeah, please go ahead.
Actually, there are a lot of problems for optimization, like flight gate scheduling and community grouping. So I think it also contains. It can also be mapped into the Cuba problem. So can we do that?
I didn't understand. You're saying that a lot of optimization. Let me repeat to see if I understood the question correctly. You're saying
There are a lot of problems like optimization. Suppose, for example, if we have a group of people and we uh, make a team of 2 teams. We have 10 people and want to make 2 teams of the 2 peoples. So can we map into the Cuba problem, like how we can arrange
Qubit
the
problem. Are you saying that can you map those optimization problems to
to
quantum
Cuba
algorithms?
problem? Yeah, Cuba problem.
Okay.
Quadrit. Yeah.
So go
Yeah,
ahead.
so yes, most of the optimization problems can be mapped to the Cubo problems. But I mean, without understanding in detail, it's difficult to answer. But yes, many of them, or rather most of them, can be done.
You might want to send a problem statement to us and look for if you were looking for very specific advice. Yeah.
Okay, ma'am.
Any other questions? If there are no other questions, I will want to remind everyone that if you have problem statements and you are interested in doing a hands-on session, then please do write back and give feedback and also mention your problem statement. This is very important because only if there are enough people who are interested in the detailed session where a specific problem statements get discussed and there's an opportunity to work online on the system, that will be arranged, right? So if there are enough people interested, only that session will be arranged, because we want to understand what is the appetite for people to actually attend a 6 to 7 hour session, right? Because it probably be at least 6 hours if we are doing a more detailed session, or at the bare minimum.
Thanks, ma'am. Thanks, ma'am. Yeah, we will attend that, ma'am.
So you need to write that, saying here,
Okay, ma'am.
just reply back. VK is asking, who do we write to? You got an invite from an email ID, please write back to that email ID. And if you want, you can CC it to Reena at QETCI, as well as Sachin. All people are marked on that email, right? Which went as an invite to all of you.
Ma'am, there was one question, I think we have missed it. So and it was from Vaishnavi, and she was asking like these sessions could be arranged in, I mean, weekend, not the weekdays. I mean, it was.
So our experience with weekend sessions is that very few people join, Vaishnavi. So today, for example, the peak team strength was around 62, right? And until, now people have started dropping off now, but otherwise we had 62 people. On the weekends, we get a lower participation. Why don't we do a quick poll? How many people? I'm just going to create a poll and send it. Second.
So I think it will be best decided if you write a mail to everyone and they will reply back.
No, I'm just creating a poll. I just created a poll.
Okay.
And I'm launching it. So there is only one question in the poll. Sessions on weekend, single choice, yes or no? Please just put in your preference. And I would request there are 39 people, please everybody put in, so at least 38 responses I should get. Only 23 responses. Yeah. Neha, if you could click on the poll, please. Poll question, it would have popped up on your screen. It's a 60-40 till now. 60% wants to do it on the weekend. So my question to, I know Sachin, your session has happened, but let's say if we do the detailed session, would it be possible to do it on a weekend?
Yeah, we can plan actually the logistics accordingly. No worries.
All right. Okay. Yeah. So looks like at least in this group, 62% now actually want the session on the weekend. All right. So that's great. If there are no other questions, I would take the opportunity to thank everybody for joining in for this very, very technical session. And a very big thank you to the Amazon team, to Sachin, especially for taking the time for doing this session. And Kratvir for doing the moderation. I know you were traveling, Kratvir, so thank you for joining in. And thanks everyone. If you have any questions, any feedback, please do reply to the email that you got the invite from. Sachin, any last points? Otherwise, we'll say bye-bye.
No, thanks, Reena. Just one point actually, guys. I'll repeat the same point that I started with actually. There's a myth that you need to be a PhD in quantum mechanics. I am from the BCom background. So it's just about about how you start and when you start. That's it. Thanks everyone. Thank you, Reena.
All right, thank you. Okay, thanks, Sridhar. Yeah, thanks. Yeah, Yukti. Yukti has a question. I have a general. Is there any group of such doing QC? Shripa, then everybody, please now, because the session is wrapping up, your messages may get lost. Please go ahead and write an email if you can for any questions that are coming in right now. We would prefer that you write an email to us so that we are able to capture all these suggestions.
Ma'am, there is one question from Yukti, and she's asking about is there any group on focusing on QEC in India?
Quantum error correction, I'm not aware of any major work happening.
And
but
she's asking for the mail ID also. It seems to have a mistake.
You can write if you either pick up the email ID that from which you got the email, or look at my email ID. I've just pasted it here on the chat window. I think the other email ID is info@qvtci.org. These are the two. All right then, so we're logging off. Thank you. Bye-bye.
Thank you, everyone.